Okay, so hi everybody. So here is the link to the YouTube stream. So this is lecture 17. Let's see here. Yeah. And today we're going to do, well, okay, so first we're going to finish inclusion-exclusion. Which we ran out of time at the end of the last lecture. And then we're going to start a new unit of the course, which is going to last 5 or 6 lectures, which is going to be probability theory. And roughly speaking, this lecture is just going to set up the basic framework and give lots of examples. And so first I'm going to talk about what I'll call classical probability, which is the way people thought about probability in like the 1500s and maybe the way you thought about it in high school. And then I'll start talking about probability spaces, which is just kind of a slight generalization of that actually in this course. So let's start by doing this. Let me just get my mouse. Okay. So let's remember what this was. So last time we stated the inclusion-exclusion theorem at the end of the lecture. So let me just restate it. So the theorem says if you have a bunch of finite sets, so if A1 through AN are a finite set, then there's a formula for the cardinality of the union of the sets. So the cardinality of A1 union A2 all the way up to AN can be written as an alternating sum in the sizes of the intersections. So first you have the sum of the sizes of the sets. Then you subtract off the sums of the pairwise intersections. And then you add back the sums over the 3-wise intersections. And so on. And if you were to write this in a single summation formula, you would get this. So it's a summation as k goes from 0 to n. Sorry, k goes from 1 to n. Of this alternating sign, -1 to the k -1, times the sum over all subsets of indices of size k. And then the intersection of the AIs for all i's in that set of indices S. So I've used a new notation here, which I'm going to use, which is used a lot in combinatorics. I'm going to use the rest of the course. So square n just means the set 1 through n, since I'm going to be writing that a lot. So that's the inclusion-exclusion theorem, which generalizes the well-known formula for the cardinality of a union of 2 sets. And let me just give you the proof. Let me just tell you what the proof is, generalizing the proof for n equals 3 that we did in the last lecture. So let's see what the proof is. So what I want to show is that both of these sides, these cardinalities are the same, right? So what I'm going to do is I'm going to think about how many times a single element is counted on both sides. So let X be an arbitrary element of this union. So we have that it's, an element of, okay, mess this up. X is an element of A1, union A2, union all the way up to AN, be arbitrary. So such an element is counted how many times is it counted on the left-hand side of the equation above in the theorem?
Once.
Yeah, just once, right? It appears once in the union. So X is counted once on the left-hand side. Now, to figure out how many times it's counted on the right-hand side, we're going to have to do something a little bit clever. So this is an element X that appears in the union of all these sets, right? So it means it appears in some number of these sets. So what we're going to do is we're going to look at the set of indices I such that X appears in AI. So let S be the set of indices. So these are the labels of the sets such that this particular element X appears in the set AI. So for example, if X appears in all the sets, this S is just going to be, or, you know, to avoid confusion, let me give this another name. This R is just going to be all the numbers 1 through n. And if it only appears in one of the sets, the set is only going to contain one element. Okay. And now assume that this set R has some number of elements, let's say T elements. Okay. So now let's begin to think how many times is X going to be counted on the right-hand side. So let's say the number of times X is counted on the right-hand side. So RHS means right-hand side. Well, let's look at this. So how many times is it counted in this first term in the sum? Well, it's a number of sets that X appears in. So that's going to be T times because it appears in T sets, right? So this number is T, but now it's also counted in these negative terms here, corresponding to pairs of subsets. This is a little trickier. So how many times is it going to be counted negatively in these pairs of subsets? Well, it's going to be the number of pairs of subset, the number of pairs contained in R. Every time you have two AI and AJ, such that X appears in both of them, you're going to pick up a -1. And X appears in these T different sets. And so the number of times you're going to get a -1 is the number of pairs, the number of 2-element subsets. Let me just be very clear, the number of 2-element subsets. So any questions about that step? It's kind of a subtle step. So I'm saying that, well, you know, X, how many times does it appear in the second red line term here? And well, every time there's a pair of indices that are both in R, you're going to pick up a -1. So that's how you get this quantity. And now, can somebody tell me what the next contribution is going to be from this term here?
That would be the number of 3-element subsets of R.
Yeah, the number of 3-element subsets of R. Okay, this doesn't need to be read. And so on. You keep alternating. So if you write this out, what do you get? Well, you get T minus T choose 2. That's the number of 2-element subsets of R, plus T choose 3 minus T choose 4, all the way up till t choose t, which is going to have a sign that's -1 to the t -1. And now, where have you seen this before? So if you did last week's homework, you've seen things like this before. Well, okay, I'll just tell you the punchline. Or does somebody remember now?
Is it reminiscent of the binomial expansion?
Yeah, if you write 1 plus -1 to the t, that's 1 minus t plus t choose 2 minus t choose 3, ... and so on. And this, of course, is equal to 0. So this implies that this whole thing is just equal to 1, which is what you wanted to prove. So the number of times x is counted on both sides is 1. And so the two cardinalities, the two numbers are equal. So any comments or questions on that proof? Okay, so the reason we did this is we wanted to solve this problem of derangements. So let me just tell you what that is. So okay, so definition, a permutation pi, which I'll write as pi1, pi2, all the way up to pi n of the numbers 1 through n, which I'm now writing as like this, is a derangement if pi I is not equal to I for every I. So it has no fixed points. And our goal was to count the number of these things. Right? So we're interested in the set D. So let Dn be the set of permutations. Or I mean, okay, let's write it like this. So let's let Sn be the set of all permutations on n elements. And let Dn be the set of derangements. So this is a subset of Sn, right? Now, before we do this, I don't know, do you think derangements are common or do you think they're rare?
Probably pretty rare.
Rare. It looks like it's pretty rare, right? That nobody gets mapped to their own position. Okay, so let's see what the answer is. Anybody else have any thoughts?
I have a question.
Mhm.
Is there a reason that we use pi? Is it just like common notation or?
It's just common notation. You know, pi is a Greek letter for p, which is like permutation. That's it.
Is that pi I doesn't equals to what?
I.
I?
Yeah, pi I does not equal to I for every I less than it. Right? Permutation maps every number from 1 to n to some other number between 1 and n. In fact, it rearranges them. And this is saying no number is mapped to itself. Okay. So let's count these. So we're going to do a trick. I'm going to define A1 to be the set of permutations which fix the element 1. And in general, I'm going to define AI to be the set of permutations which fix the element I. And now I'm going to observe that the set of derangements is just a set of all permutations minus the permutations that have a fixed point. And if a permutation has a fixed point, if and only if it fixes 1, or it fixes 2, or it fixes 3, or it fixes n. And so the cardinality of the set of derangements is the cardinality of the set of all permutations minus the cardinality of the set. Which, so now if we, so by the way, so we know the cardinality of the first set, right? What's the cardinality of Sn?
Shouldn't it just be n factorial?
N factorial, number of permutations of n elements. So if we can, that means if we can estimate the cardinality of this union, we'll have the number of derangements, right? So we want this. So now we're ready to do inclusion-exclusion. So by inclusion-exclusion, we have that this cardinality of the set of permutations which have at least one fixed point is this sum, right? K goes from 1 to n minus 1 to the k minus 1. Sum over all subsets of indices of size k. So sorry, I haven't been writing the subset equals everywhere. I should do that since I'm, yeah, I want to be very, I mean, often, okay, later in life, sometimes you don't write that, but let's be consistent here. Times the cardinalities of these intersections. So this reduces the task of computing the cardinality of the union to computing cardinalities of intersections. So now the goal is to compute these. And if I can compute those, I can plug them into the formula and get some expression. So let's do some examples. So what's the cardinality of A1? So what is A1? A1 is the set of permutations which fix the element 1. So 1 gets mapped to itself, and then the rest can be any permutation. So how many such permutations are there?
-1 factorial.
Yeah, you just choose the rest of the, you just make a permutation on the rest of this stuff, right? The n-1 coordinate here. So this is n-1 factorial. What about A1 intersect A2? So that's permutations which fix the first 2 elements.
n-2 factorial.
n-2 factorial. So in general, if you fix k elements, then the size is going to be n-k factorial, right? So in general, if you fix any k element, if you fix the elements in a subset S, the cardinality is going to be n minus the cardinality of that set factorial. Because you just, you know, those are fixed and they're n minus that cardinality remaining other elements. So that's what we wanted to calculate, right? So we did this little side computation here. And now we can plug in this into the formula. So you have a summation, k goes from 1 to n, minus 1 to the k minus 1. And now you have a summation over all subsets of indices of size k. And now you've computed this number here. And the beauty is it doesn't depend on the set. It's just n minus k factorial. So okay, that's not a very clean answer yet. Let's figure out what that sum is. So okay. So I have a sum of just the number k minus n minus k factorial over a bunch of subsets here. How many of those subsets are there?
N choose k.
N choose k. Just all subsets of k elements chosen from n elements. So this is summation, k goes from 1 to n, minus 1 to the k minus 1. And now I just multiply this number by n choose k times n minus k factorial. And now, you know, now I can plug in what n choose k is. So this is k goes from 1 to n, minus 1 to the k minus 1. I have n factorial, k factorial, n minus k factorial times n minus k factorial. I get a nice cancellation here. Okay. And now, I can rearrange these terms. I get that I can pull the n factorial out on the front since it doesn't. So, okay, this is another principle of manipulating summations. This n factorial, right? This doesn't depend on k. So it's just a constant as far as the summation is concerned. So I can just pull it out in front. It's like multiplying everything by 2. So I get that this is n factorial. And now I just get summation k goes from 1 to n minus 1 to the k minus 1 times 1 over k factorial. So that's not the number of derangements. That's the number of permutations that have a fixed point. So to get the number of derangements, I have to subtract this from n factorial. So this is n factorial minus this whole quantity. So many of you may be new to summation notation. That's okay. It's okay if you're a little uncomfortable with this notation. It might be worthwhile to go over this a few times because this is a good example of how to use this notation effectively. So anyway, when you do this, when the dust settles, what do you get? You get that this is n factorial times 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial dot dot dot. You get a minus 1 to the n, n minus, sorry, do you get, minus 1 to the n minus 1, sorry. One over n factorial. Now that's not that nice, but does that remind anybody of anything they've seen elsewhere?
It's the Taylor expansion of e to the minus 1.
Exactly, yeah. So recall that e to the minus 1 is 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial forever. And these Taylor expansions converge pretty quickly. So what you get is that this quantity is about equal to n factorial divided by e. So actually, there are a lot of derangements. 1 over e, that's about 37% of all permutations are derangements. So this is about 0.37 times n factorial. So the conclusion is about 37% of permutations are derangements, which I find surprising. I find it to be surprisingly many. So any comments or questions about that? Okay. So now we're going to move on to chapter 7, probability, which is one of the most useful things, maybe the most useful that you learn in this course. And there are a number of ways to say what this is. One way I describe it is it's a precise way to reason about uncertainty. About certainty or uncertainty, they're just flip sides. Other words people use are likelihood, risk, etc., etc. And the precise is very important. So people have been thinking about these things forever. Life is very uncertain, and people have been thinking about these things intuitively for a long time. But really, this was developed starting maybe in the way we know it in the 1500s in the context of gambling, where the uncertainty is somehow very concrete. And this is something we encounter, all the time in life. For example, here are some some statements that you might come across. So you might say, well, the chance of a flush in poker, which is a card game, I'll say exactly what this means later, is 2 in 1,000. Okay, that's a concrete statement that comes up if you go gambling. That's a statement about probability. And then you hear other statements that are maybe less precise. So the the chance of an earthquake in Northern California in by 2030 is at least 30%. That is some statement about certainty or uncertainty of something happening. But these are it's not so clear what the second statement means. In both cases, there's a notion of chance, but these notions seem to mean different things in the two cases. Then I don't know. I mean, with COVID, we hear about probability all the time. That what are the chances of getting sick given that you have done X, Y, and Z other things. So this comes up a lot in in medicine. Comes up generally in all aspects of statistics. Comes up in computer science and randomized algorithms. And if you do any kind of machine learning, it's ultimately based on probability. So it's an extremely useful thing also in these various academic pursuits. And what we're going to do in this lecture is set up the framework. We're going to define what probability even means, because it's a very slippery concept, actually. So we're just going to set up some basic notation and do a few examples. So let's start off with a simple example. So example 1. So suppose you flip 2 fair coins. So that means they're equally likely to be heads or tails. What is the chance they are different? So, which means one is heads and one is tails. Okay, so how would you solve this question intuitively? Any thoughts?
We could enumerate all of the cases and then basically count.
Great, enumerate all the cases and just count them, right? So possible outcomes. Well, so fair coins, let's say that they can be heads or tails, and let's denote that by H or T. So possible outcomes are there are 2 coins. So there are 4 possible outcomes. Either both are heads, or the first is heads, the second is tail, or the second is tails, the first, the second is heads, the first is tails, or both are tails. Okay, so then that's a description of all possible outcomes. And then what are we interested in this particular example? We're interested in what is the chance that they are different. Well, in 2 of these outcomes, they are different. So let's call these the successful outcomes. So it's just HT and TH. And then we're making an implicit assumption here. So they're fair coins. And so the implicit assumption is that these are all equally likely outcomes. And so then the probability of success is the number of successful outcomes over the number of all outcomes, which in this case is 2/4, which is a half. So there's a 50% chance that you're going to get two different coins if you flip two fair coins. So any comments on this before I go on to formalize it?
I have a question.
Uh-huh.
Why is heads tails and tails heads different? Are we saying that it does depend like which coin is which?
Right. So in real life, the coins are distinguishable, right? Like there are actually two coins.
Okay,
So
I see.
so this is different from the basic counting in that yeah, you're asking a really good question, and I'll just formalize it actually. That's the next thing I'm about to do.
Okay, thanks.
Okay, so let me, any other comments before I get some definitions? Okay, so here are the basic definitions of probability. Okay, so an experiment, sometimes called a random experiment, but an experiment is a well-defined procedure with a set of possible outcomes. And you could define it the other way, an outcome is a complete description of the result of an experiment. I mean, I guess the thing being defined here is the word outcome, so I'll just underline that. So for example, in this example, what's the experiment? Well, the experiment is that you flip two fair coins. And what are the outcomes? Well, the outcomes are these four descriptions of all the possible things that can happen when you do this well-defined process. You flip two fair coins, and the word fair says that, you have a 1/4 chance of each of these things coming out. Or, okay, you have a half chance of being heads or tails. We'll say a little bit more about how to multiply probabilities later, but these are all equally likely. So in this case, the set of these are the outcomes, and the set of outcomes is very important. That's called the sample space. So in the example above, what's the sample space? Well, it's going to be this set. So that's a set in the sense that we've been learning about sets. Okay. And then within the sample space, usually you're interested in some particular subset of the outcomes, and that's called an event. So this is just terminology. So an event is a subset of the sample space. So in this example, let's call this sample space S, and then this is an event, E. This is a particular event. There could be other events. What are some other events described in words related to two coins?
Two sides are the same.
The two are the same. So yeah, for another example would be the event, let's call it E2, is the event HH and TT, and this corresponds to both coins are the same. So you have many different events. And then given these things, So in classical probability, this is like just probability that's basically a rephrasal of counting. So you have two more assumptions. The assumptions are, so one is the sample space S is finite. And the second one is that all outcomes are equally likely. So under these assumptions and under these definitions, you define the probability of an event is just the ratio of the sizes of these sets. It's often denoted P of E with this like bold P here is just the ratio of the cardinalities of these sets. So in the example above, the probability is a half. So this is just a formalization of this example. And by the way, the probability is always between 0 and 1. Why is it always between 0 and 1, given these definitions?
It's either 0% to 100% chance of the event happening.
That's true. That's how we think of it intuitively. But let's now think about these definitions.
The ratio of the cardinality of the subset is within the achievable to the cardinality of the sample space is within the range of 0 to 1.
Exactly. So E is a subset of S. So cardinality of E is less than the cardinality of S. So this probability is between 0 and 1. Always between 0 and 1. So what Olivia said earlier, that it's the chance is always between 0% and 100%. That's correct intuitively. But what we're going to learn in this unit is how to move from intuitive thinking to formal thinking within this framework, because it's very easy to make mistakes with intuitive thinking. So these are the basic definitions. They're kind of boring. There's not really a new concept here. But let's do a few examples just to make sure we understand how to set up the experiment, the sample space, event for different problems. These are the concepts. So this is the framework we're going to use. So any questions before we move on? Okay, let's do one more example. Or let's do a few more examples, actually. Here's another example. So we flip 10 fair coins. What is the probability of getting exactly 5 heads? So again, it's heads or tails. Okay, so we're going to analyze this using this rubric here. So first, what is the experiment? So what's the experiment in this setup?
We are flipping 10 fair coins.
We're flipping 10 fair coins. So this is the experiment. Okay, the second thing is, what is the sample space? The sample space S. Well, you have to make a modeling decision, right? You're given something in English, you have to turn it into some kind of formal symbols. Let's use the same as we were doing earlier. It's a string of H's and P's, where the ith position tells you what happens with the ith coin. So this is going to be a set that looks like this. It's going to be, let's say, S1 through S10, where Si is either heads or tails. Another way of writing this is just the set H comma T raised to the 10. It's a Cartesian product of the set with itself 10 times. Now, one difference here is we're not enumerating the elements of the set. I mean, it would have 2 to the 10 elements, right? It would have 1,000 elements. So this is one difference with the previous example. We don't have to explicitly write the sample space every time. Okay, so that's item 2 on the list. Check sample space. Item 3 is the event, and that is this getting exactly 5 heads. So now we need to define the event. And again, we need to follow this rubric. So what is the event? It's a subset of the sample space. So it's a set of all strings of length 10 in the sample space such that what happens?
5 of the results are heads.
Yeah, and the rest are tails. So okay, good. So now we've defined our 3 things, and now, okay, in this example, because of fair coin, we're meeting these assumptions. The set is finite, outcomes are equally likely. So the probability, in this case, the probability of this event is just the ratio of the cardinalities. So it doesn't depend, it just depends on the sizes. So now we have to estimate the sizes. So what's the size of S? Well, we've done this many times. It's 2 to the 10. And what's the size of E? Anybody see something they've seen before here?
It's like the number of 10 bit strings with 5 ones. So 10 choose 5.
Yeah, 10 choose 5. And so this answer is just 10 choose 5 over 2 to the 10, which yeah, I don't actually know what it is. It's decently large. I think it's
252 over 1024, I think.
so it's about 25%. So there's actually that's higher than I thought too. There's about a 25% chance that you get exactly 5 heads. So it's really quite likely. It's actually the most likely outcome. Not surprising. We'll see how to, well, easily prove that later. But it's a simple example, but what I'm trying to drill in here is these 3 key concepts of experiment, sample space, and event. Okay. Let's do another gambling related example, since I guess this is where this comes from. Okay, so I asked this question, what are the chances of getting a flush in poker? Or did I ask that? I asked that somewhere here. Yeah, okay, so what is a flush? So a flush is when you draw 5 cards and they're all of the same suit. So a flush is 5 cards of the same suit. I think that's what let me just double check. Actually, I haven't played poker in a while.
That's what it is.
That's what it is, right? Okay, good. I always get confused with the word, but okay, that's what it is. So suit again means you have diamonds, hearts, clubs, and spades. So there are 4 suits, and then there are 13 ranks within each suit. So there are 52 cards. Okay, so what are the odds of being dealt a flush in poker? This is a very practical question that comes up if you play poker. So again, okay, what's the experiment? What's the experiment here?
Just drawing 5 cards.
Yeah. Are they ordered or unordered?
They are unordered.
Okay. Now we have a choice here. We could have made the sample space ordered. We could have done that. And everything would have worked out. But because in poker, the order doesn't matter, we can start off defining the sample space as being unordered. So there is a choice to be made here. But let's do unordered. Okay. Now what's the sample space?
The question asking the odds of being, what is that?
Sorry, yeah, okay, odds, yeah, okay. Let's just say what is the probability? I think odds is just a word.
I know the meaning of that. I just don't understand like what is
Dealt.
flush.
Oh, okay. So flush. Okay. So you're being dealt 5 cards. So what is the probability that a hand, or that I mean, okay, yeah, that a random hand of 5 cards is a flush. So flush is defined over here, right? So there are 52 cards, and 5 cards are flush if they're all the same suit. Does that answer the question?
So it's like 5 same like diamonds.
Yeah, 5 diamonds or 5 clubs or something like that.
And are we including like straight flush and royal flush in this?
Yeah. This is just any flush.
Okay.
Okay. So the sample space, because the outcome is only unordered sets of cards, I'm not keeping track of the order. The sample space S is the set of all subsets of 52 cards. So let's label the cards 1 through 52. And you have 5 of them. So label the cards. Okay. And that's all possible outcomes because I'm not recording the order in this case. Now what's the event? E. Well, okay, so it's a set of all hands that are flushes, right? So any ideas about how to, it's just a counting problem now. I mean, but how do you choose a hand that's a flush?
First, you choose the suit, so that's 4 ways, and then within a suit, you choose 5 from 13.
Exactly, yeah. So this E is actually a union of 4 sets: E sub B, E sub H, E sub C, and E sub S, where E sub B is the set of all S. Oh no, I shouldn't have used S. Sorry, this is very bad. Don't use the same letter twice. It's really bad. Let's call this H for hand. So it's a set of all hands in the sample space such that H has only diamonds, and so on. Good. So I defined the experiment, the sample space, and the event. And now the probability is the ratio. I'm assuming all these are equally likely. The probability of my event is the ratio of these cardinalities, which is which I now have to figure out. So what's the cardinality of this set?
52 choose 5.
52 choose 5. What's the cardinality of this set? Well, okay, it's a disjoint union of 4 sets. So it's 4 times the cardinality of each one of those sets. And in each one of those sets, you already chose the suit, and there are 13 cards within each suit. So it's this times 13, choose 5. And so the answer here is that this is 4 times 13, choose 5, divided by 52, choose 5, which when the dust settles is indeed 2 over 1,000. Okay, so the difference in this example from the previous examples is that I deliberately made the sample space unordered. I actually forgot a little bit of information. And I'm allowed to do that. So in the description, it says a complete description. So complete description means, of all the relevant features. And I'm always doing some kind of abstraction, right? If I really flip 2 coins in real life, there's actually a ton of information, like where on the table did it land? How long did it take to, how many times did it oscillate before it settled? There's all kinds of information, right? But when I set up the sample space, I'm only storing the relevant information. So that's why it's, this falls in the same framework. So any questions or comments about this?
So I just wanted to say, like, if in this case, like originally, it can be unordered, but if it's also ordered, then it works too, right? Like
Yeah,
if
it
we
totally
consider-
works if it's ordered. Yeah. So remark, this would work if it's ordered. You just have to cancel some 5 factorials. And sometimes it's easier to add structure to the sample space, actually. In this case, it wasn't. So there is an art to choosing the sample space. You want to choose it in a way that you can do the counting easily. So in general, you want to choose S so that it has the relevant information. For the event you're interested in, right? Like if you were playing a game of cards where the order mattered, then you would have to use an ordered sample space. Otherwise, you couldn't even write down events that talk about the order, right? So to express the event E, choose S so that it has all the relevant features, I suppose is the right word. And 2, so that the counting problems are easy.
So if we use ordered hands, the answer will still be the same.
Yeah, it will be the same.
E
You'll just
will
end up
also be
dividing
ordered.
by 5 factorial in both cases.
Oh, okay. So, yeah, I have a similar question of this. So, if this is not asking like 5 cards in the flush, it's like if it's like picking 4 cards and the 4 cards are different, like 1D, 1H, 1C, 1S. So will that be 13 times 13 times 13 times 13 or 13 plus?
Well, that's a question about counting. So, I mean, I don't know off the top of my head, but I would say try to use the methods we learned in counting in the last 2 or 3 lectures to answer that. It's a good question.
Okay.
Yeah. Okay, so let's do one more interesting example, which comes up a lot. It's called the birthday paradox. So example 4. And the question is, what is the probability that 2 people in your section, let's say a section has 30 people, have the same birthday? Okay, now this is a little different from the previous examples because it's not clear what the experiment is. So this is why I'm stressing this, that sometimes people ask questions like this. Always ask, what is the experiment? So what's the experiment here?
Just choosing 2 people from your section.
Choosing 2 people from your section. That's a good. That's a very good option. So choose 2 people. So let me make it clear that some 2 people, that there exist 2 people in your section with the same birthday. So it really, this is actually more of a question about the whole section. That are there 2 people in there that have the same birthday? So this is not actually quite the right experiment.
We could assign a birthday to each different person.
Yeah. So I mean, this is a modeling question. It's not a math question yet. And so both answers are valid, but really what's meant by what I meant to say, and what maybe, well, it's good that I'm forcing myself to write an experiment now, is the experiment here is that you assign each person a birthday in, let's say, the 365 non-leap year days of the year, uniformly at random. So this experiment is actually done before you were all born, or whoever was in the section was born. So uniformly at random is a phrase that's used a lot. It just means all outcomes are equally likely. Okay. So this is very important, because until I know the experiment, it doesn't even make sense to talk about probability. So this is usually what's meant in the birthday paradox. There's an underlying modeling assumption, right? So this is an underlying model of reality that's used to derive this. And this comes from somewhere, right? This is part of setting up the problem. Okay, so let's assume you have 30 people in the section and each person has a random birthday. I don't actually know if that's true. I think it's not quite true, but something like it is true. What's the probability that 2 people have the same birthday? So that's the experiment. So now what's the sample space?
Would it be like all 360, well, like the birthdays that you assign the 30 people, correct?
Yeah, so one way to think about it is it's the set of all birthdays raised to the 30. Because for each person, you get to choose a birthday. So it's an assignment of birthdays to people, right? So this is and by the way, should this be ordered or unordered?
Ordered, I think.
Yeah, why?
Because each person is distinct.
Yeah, the people are distinguishable. The people are labeled. So good. Okay. Now, what's the event? Or yeah, what's the event? Well, E, so this is the set of all, I guess, assignments of birthdays such that 2 of them are the same, right? Such that there exists some I not equal to J, such that Si equals Sj. So there exists some 2 people with the same birthday. Okay. So now we're going to, well, now we know how to calculate the probability. The probability is a ratio of the cardinalities. So the cardinality of the first set is easy. What's the cardinality of S?
30.
60.
Oh, sorry.
Go ahead.
60?
60, not really, right? So
Is it 30? Sorry.
no, so remember, this is the set of all words of length 30 where each letter has 365 options. So how many ways are there to choose such a word?
It'll be 365 to the 30.
Yeah, because there are 365 ways to choose the first one, then 365 ways to choose the second one, and you multiply them by the product rule. So 365 to the 30. So there are lots of different assignments of birthdays to the people in this section. So by the product rule, let's say. And now the cardinality of E is a little bit trickier. So I'm going to do a trick that I did earlier. So the probability of E is cardinality of E over cardinality of S. Now I'm going to use this general fact, which is the probability of any event plus the probability of its complement is what?
1.
Because the sum of the cardinalities of the set and its complement are the cardinality of E. So I'm actually going to use the complement. This is a very common trick. The probability of E is 1 minus the probability of E bar over 1 minus the probability of E bar. And now E bar is this kind of set which is actually easier to count. So this is the set of all sequences of 30 numbers lying in this set 1 to 365. Let's write it using our shorthand notation, which are all distinct. Right, so no two are the same. Anybody know how to count arrangements of 365 objects into 30 objects that are all distinct?
365 choose 30.
Okay, so somebody said 365 choose 30. That's not quite right because that's the number of unordered ways. Yeah, the permutation, right? So P 365 30, which is 365 factorial over 335 factorial. And so now, oh, sorry, this is cardinality of E. This is not E. So, right, the cardinality of E is this, of E bar is this. So then the conclusion is that the probability of E is 1 minus this ratio. So 365 factorial over 335 factorial divided by 365 to the 30. And if you figure this out, I mean, I haven't exactly calculated this, but it's actually very high. It's bigger than 90%. Okay. So this is called the birthday paradox. And it's a paradox because you feel like, oh, there are 30 people. There's so many different birthdays. There shouldn't be 2 people in the same class with the same birthday, right? This is very far from the situation of the pigeonhole principle. You only have 30 people. It's very easy to assign all of them a different birthday. But if you do it randomly, then it's very likely you're going to have a collision. That's what this is saying. This is called the birthday paradox.
Could you explain why is it permutations again?
In for E bar or in the beginning?
I think both. I don't understand why is it not.
Okay, yeah. So roughly speaking, the reason it's permutations is that the position indicates which person, right?
Yeah.
So that means the order matters, right?
But we're just assigning them birthdays.
Right. Okay. So I see. So you raise a good point. You're saying, what if you tried to do this with an unordered sample space, right?
Yeah.
Yeah, that's a very good point. You could try to you could try to do that. So remark, you can try to do this with an unordered sample space. So that would just be, you just count the frequencies. So you're basically throwing 30 balls into 365 bins, and you're asking what's the probability that no bin has 2 balls, right?
Yeah.
You can do that. It's harder. So it works, but harder. So it's the same principle as before, that you should choose a sample space that contains all the relevant features and for which counting is easy. So in this case, the ordered one is much easier. Good question.
If the two people call one A and B, so we do A first and then do B is different from we do B first and we do A.
Yeah, I mean, if you're really treating the people in the class as people, then the people are distinguishable, right? They're labeled.
Yeah.
Yeah. So these are all great questions. And in general, you should be mindful of this. When you choose a sample space, you want to use ordered or unordered. Okay, so that's all I want to say about this classical probability for now. Now I want to introduce the concepts of, I guess, what the book calls probability theory. And this is just a slight generalization. And the motivation is, well, what if all the outcomes are not equally likely, right? So you need some framework to handle those situations as well. And let's now define this framework. So the definition. So the concepts of experiment and sample space and event are still relevant. But now a probability space consists of a sample space S with a probability distribution. B, which is a function from the sample space to real numbers, which satisfies 2 properties. One is that the probability of any point in the sample space is between 0 and 1. And the second is the sum of the probabilities over all points in the sample space is 1. Okay, so this is the intuitive meaning of these numbers, these probabilities. So P of S is the likelihood of outcome S in the sample space. That's what the intuitive meaning of this probability distribution is supposed to be. And then given these definitions, the probability of an event E is, use this bold P again. P of E is just the sum of the probabilities of the outcomes in that event. So what's the new thing here? Everything here is the same, except there's a probability distribution. And in the background, you always have this concept of an experiment sitting in the background. You still need a concept of experiment to even define. I mean, usually this always comes from an experiment. So that's a probability space. And this includes the old example, right? So if I were to write this classical probability as a probability space, what would the probability distribution be? So if all outcomes are equally likely, then what would this probability distribution function be equal to?
Is S is equal to 1 over the cardinality of S?
Yeah, it's just equal to 1 over the cardinality of S for all S in the sample space. So this equally likely, this is the so-called classical probability, although nobody really calls it that, but in the book it's called that. So this is the only generalization. So I'm going to use this to analyze a famous problem about which books and newspaper articles and all sorts of things have been written, called the Monty Hall problem. So any questions about these definitions before I do that? Okay, so let me describe the Monty Hall problem. So the Monty Hall, this is actually a game show that used to take place in the 70s. And in the game show, you have 3 doors labeled 1, 2, and 3. And the following happens. So first is a car is randomly placed behind one of the doors. Uniformly at random. You don't get to see this. And the other 2 doors, there's a goat. So hidden behind these doors, let's say maybe a car ended up here, and the other ones, there are goats. But you don't get to see this. Then the contestant, you, see these doors and choose one. Let's also assume randomly, since you have no information. You don't see anything. So you choose a door, also randomly. This is a modeling assumption. You might as well assume it's random since you have no information. And then here's the twist. So Monty, which is the name of the game show host. So you choose a door randomly and open it. Okay. Now, if you get the car, you win. But if you open it with a goat, sorry. Well, I've got this wrong. You choose a door randomly and do not open it. You just choose a door randomly. You don't open it. You don't know yet. So let's say you choose this one. And that now what Monty does is Monty opens one of the other doors and reveals a goat. Okay, so there are 2 other doors remaining, right? Still everything is hidden. Monty is going to open one of these and show you a goat. And now the question in this game show, which made it very exciting, is should you switch your choice or not? Okay, so that's called the Monty Hall problem. Let me add some more pages here since I'm running out. So in the meantime, let's form some thoughts on this. Should you switch or not?
I don't remember the exact reason why, but you should always switch.
Okay. Does anybody have any intuitive reasoning about this? About whether or not you should switch?
If there were...
Well, the first door would have a 33% chance, and if one of the other two doors, which also have a 33% chance each, if one of them's canceled, then the one that you switch to would be 67%.
Okay, that's a very good thought. Anybody else?
If you picked a goat, then you know that then assuming that you picked a goat, you know that the other one that's still remaining will be correct. So if you picked a car initially, then you know it's changing it to the wrong answer. But there's a higher chance that you picked a goat, and if you did pick a goat, then you will definitely be correct by switching.
By switching. Okay, so everybody seems to think you should switch, which is very impressive because most people's answer to this is, well, you haven't seen anything. And you know, the car is equally likely to be behind the door you chose and the door you're going to switch to, so it doesn't make a difference. Now, the correct answer is you should switch. Although as recently as, you know, in the last few decades, people have still been writing articles saying that it doesn't make a difference. But this is why it's so important to follow the framework of probability, because we're running out of time, but we're going to set up a framework where we're just going to calculate and prove that you should always switch. So again, what's the experiment? Well, the experiment is these three steps, right? So experiment. Steps 1 through 3. And this is a little underspecified because it says opens one of the other doors. So let's say opens one of the other doors, opens one of the other doors with a goat behind uniformly at random. Right? So no matter what door you choose, so you choose one door, one of the other doors, at least one of them has to have a goat. Maybe both of them have a goat. Well, Monty opens one of those uniformly at random. So this is now a well-defined experiment. This is the experiment. And now the most interesting part of this is what's the sample space? What are the possible outcomes? So now you need to think about how to formalize this. So what are the relevant features? Well, there are really three choices in this problem. One is the car is placed somewhere. The other one is you choose a door. And the last one is Monty opens a door. So the data are, so it's going to be two poles that I'm going to call car, you, and Monty. These are the choices. Each of these is going to be a choice of a door. But then there are some constraints. So the car can be placed anywhere. Once the car is placed anywhere, you can also choose any of the doors. But Monty is never going to open a door with a car, right? That would ruin the game show. And Monty is also not going to open the door that you opened. So there's some constraints on which door Monty chooses. Monty is not equal to the door you chose, and Monty is not equal to the door the car is under. Okay, so that is the set of all outcomes. And the event you're interested in is, well, should you switch? Another way of saying that is, what's the likelihood that the door you chose has the car? So the event you're interested in is, it's a set of all tuples such that you chose the car. Now, I'm out of time, so I won't be able to calculate the probability. I'll do it next time. But we've already achieved a lot by setting it up this way, right? We've turned this problem, which is mysterious because it's not so clear how much choice you have. And it's not clear what is still random and what's fixed at what point in this procedure. By defining this experiment precisely in this way, you've turned this into a counting problem. Right? So these are all possible outcomes. Oh yeah, sorry, we haven't figured out the probabilities. Okay, we have to do that. We will do this next time. But then once this is done, okay, you can prove that it's always better to switch. And this is a highly counterintuitive phenomenon, which it's very difficult to be sure that you reasoned correctly about, other than by following this rubric. So anyway, that's it for today.
So you just renamed the three possibility is that the door that has the car, the door that you pick, and the door that Monty open it.
Yeah.
And the sample space is the total outcomes that can the total result, but can't there be a possibility that you just pick out the car,
Yeah, no, there can be, and that's what you're trying to understand, right? You're trying to find, so you don't get to open the door, right, until you decide whether to switch or not.
Yeah.
This is another important feature. In the experiment, you don't open the door, right? Once you open the door, the game's over. There's no more uncertainty. What you're trying to figure out is, under this process, what's the chance that the door you opened has the car versus the door that the other door that's still unopened has the car.
So so the thing that you write down, the sample space, so there are only two possibilities?
No. There are a lot of possibilities, right? These are strings of numbers with three numbers in them, right? So for example, we'll write it down next time in detail, but for example, one possibility is the car is behind one, you open one, and Monty opens two, right?
Oh.
Or for example, the car is in one, you open two, and then Monty opens three. These are all possible. I mean, I will enumerate them next time. But that's the kind of thing that's in the sample space. So you're using the sample space to encode the possible random outcomes of this process.
And the E is just the first time that you pick the car equals to you.
Yeah, E is the event that the first one that you chose is equal to the door that has the car.
Then it's just simply 1/3, right?
Well, so not right. So okay, I see. Yeah, okay. Maybe car equals you. You're right. Yes, the probability of E is 1/3. So let's see. Have I already messed this up? So let's see. Yeah, no. I think the probability is going to be 1/3. You're right, but
because the sample space is that you have three different outcomes, 1, 2, or 3, and you can only pick one, so it's just 1/3.
Yeah, no, that's a perfectly valid calculation. You're right. So you did something clever, which is you ignored Monty, and you realize that even in the first two, that the event car equals you only depends on the first two steps. And so the probability of this event is 1/3. And then, well, that implies that the probability that car does not equal you is 2/3. And that's why you should switch. So that's actually a perfectly valid resolution of this problem. But next time I'll do it in sort of maybe full detail by writing out the whole sample space. But your reasoning is absolutely correct.
So
and it's also what Faraz said earlier.
So I'm just saying because the first time you got the car is 1/3, so you don't get the car is 2/3. But if
Yeah.
they open a door and it's like a gold, because it can be a car. So if they open a gold gate, which means if you change, you have like at least 50% chance to get is bigger than 33.
Right. Well, no. So again, so that is a little bit wrong. It turns out that the probability that the car is behind the other door is 66%. But again, I think we're on the right track. But this conversation is exactly why we need to maybe write everything down, just so we can be sure. But,
Got it. Thank you.
Thanks.
Oh, and